Good morning, my name is Richard Birley. I work in the Industrial Decarbonisation Group at the Materials Processing Institute, focusing on industrial decarbonisation, fuel and energy switching, prototype design, build, installation and testing. Today I would like to talk to you about decarbonising hydrogen for DRI feed. The steel industry contributes between 7 and 9% of the world's CO2 emissions. However, to meet emissions targets by 2035 and 2050, the steel industry will need to change their production methods. Efficiencies can be made across the industry and processes to reduce energy and carbon usage. Energy efficiencies alone, however, will not achieve the 80% reduction required. Large amounts of fossil fuel are consumed to produce steel. If these could be replaced, then significant reductions in emission could be achieved. An option for fossil fuel replacement is hydrogen as a fuel and as a reductant. There are many routes for the production of hydrogen. Has hydrogen revolution begun? Across the EU, they're introducing hydrogen production. And by 2024, they're anticipating installation of 6 gigawatts of electrolyzers, and that can produce 1 million tons of hydrogen. By 2030, they're expecting that up to 10 million tons of hydrogen. Large-scale deployment of renewable hydrogen across all industry is anticipated. At these scales of production, it may be possible to use hydrogen and replace fossil fuel in industry. So production of hydrogen for the steel industry. Global production of steel is approximately 1.8 billion tons per year. Steel production through the direct reduction furnace and electric arc furnace route equates to about 108 million tons per year. Emissions from the electric route of steelmaking is already lower than that from the integrated route at approximately 0.6 tons of CO2 equivalent per ton of hot metal compared to 1.8 tons of CO2 equivalent per ton of hot metal from the traditional routes. The electric process still utilises large quantities of fossil fuel in the form of natural gas and some carbon for carburization. The natural gas may be able to be substituted with hydrogen as a reductant. The production of hydrogen as a fuel from electricity may not be cost effective, as heating could be provided directly from the electricity supply rather than using electrolysis that has some efficiency losses. However, hydrogen may still be used if there are some chemical or reactive benefits to the use of hydrogen as a fuel. So methods of hydrogen production. Methane steam reforming is the traditional method, reforming natural gas or methane. Autothermal reforming is an adaptation of methane steam reforming. Gasification of coal and biomass, pyrolysis and electrolysis, using conventional electricity and renewable electricity or power. So steam reforming. Traditional steam reforming processes fossil fuels using steam to produce a stream of hydrogen. Carbon dioxide and methane are combined to produce syngas. These reactions are endothermic and require 206 kilojoules per mole of hydrogen produced. The carbon monoxide can be further reacted with water in the water-gas shift reaction to produce carbon dioxide and hydrogen. The water-gas shift reaction is exothermic, and therefore some scavenging of the 41 kilojoules per mole of energy can be achieved, making the process slightly more efficient. Processed sustainable biomass may provide a renewable alternative to fossil fuel steam reforming. Autothermal reforming is a method of steam reforming that uses high levels of oxygen. ATR also produces syngas and water. The water can then be used in a secondary reaction to produce further hydrogen, again in a water-gas shift reactor. The oxidation process is exothermic, releasing heat as a byproduct, whilst the syngas leaves the reactor at 950 to 1100 degrees C. This heat can be scavenged and used to put back into the process. With both steam reforming and autothermal reforming, the use of CCS may provide a method of reducing emissions from these processes. Gasification. Gasification can be carried out on several feedstocks, including biomass, domestic and commercial food wastes, and fossil fuels. Syngas is the desired product. There are secondary products that are produced as well, which are tars, charcoal, chars, heat, and lignin when using biomass as the feedstock. This flow chart shows the process of gasification. We go through the drying stage. The intention of this is to remove the moisture. However, some low volatiles are lost at this stage as well. Then moves on to pyrolysis, which is heating without air. This releases volatiles and produces a biochar as well. This process again is endothermic. Oxidation then takes place between 800 and 1200 degrees C by adding air and O2 for oxidation and combustion. This process is exothermal and releases more hydrogen during the process. The final stage is reduction, where the heat is taken down to 650 to 900 degrees C, and the conversion of the remaining products can go into making producer gas. Again, this process is endothermic. So, on to electrolysis. So we have hydrogen water electrolysis. So electrolysis is a process of electrochemically separating out the constituent parts of water, hydrogen and oxygen. For electrolysis to be green, the electricity needs to come from renewable and sustainable sources. The use of hydroelectricity may be an option. However, the source provides a base load of power in many countries, and so may not be the ideal option for electrolysis. The use of off-peak wind and solar may be viable options as an electricity supply for the production of hydrogen, providing a cheap and effective method of production. Whilst we only consider the electrolysis for hydrogen production, a secondary product of oxygen is a highly valuable commodity and, if handled correctly, could be considered a second revenue stream. So some methods of electrolysis. We have solid oxide electrolysis. So the solid oxide electrolysis produces hydrogen at the cathode from water, with O2 passing through the diaphragm and being released at the anode. The system operates at high pressures and temperatures of 1000 degrees centigrade. Some laboratory scale equipment is operating at lower temperatures in the range of 500 to 850 degrees C, where efficiencies have been recorded at 90 to 100%. The lower we can get this temperature, the better for the productivity. Alkaline water electrolysis. AWE is an established technology operating at temperatures of 30 to 80 degrees C, with equipment in the megawatt range are in operation. Alkaline solutions of potassium hydroxide and sodium hydroxide are used. Hydrogen is produced at the cathode from water. Hydroxyl is passed through the diaphragm, and O2 is then produced at the anode from the hydroxyl. AWE systems are in operation at between 70 and 80% efficiency. Polymer electrolyte membrane systems. PEM are an established system that can be used for electricity production as fuel cells if the hydrogen is of a pure grade. PEM have typical efficiencies of 80 to 90%. However, the hydrogen purity is 99.99%, which is suitable for any area within industry. Water is separated at the anode, where O2 is released. Hydrogen ions then pass through the diaphragm, and the hydrogen is produced at the cathode. Electrons are passed during the process, which can be used to partially supply power to the operation. So advantages and disadvantages of these three types of electrolysis. So the PEM has high efficiency and high purity of product. However, although some of it is established technology, some of the techniques now being used are classified as new technology. They have low durability and high costs. AWE is an established technology. It has energy efficiencies of 70 to 80% and uses non-noble catalysts. However, it does have a low current density and low purity of product. The SOE system has a high efficiency, 90 to 100%, non-noble catalysts at high operating pressures. However, these are only at laboratory scale at this time and have low durability. So how would hydrogen fit into a direct reduction process? On the left, we can see the traditional method where we have iron ores fed in. These are processed and fed into the shaft furnace. Gas preparation or coal preparation to produce syngas is also fed in as the reduction agent. From the output, we can get hot briquetted iron or cold briquetted iron. Hot briquetted iron can be fed straight into an electric arc furnace. Cold briquetted iron can be fed in direct into an electric arc furnace, but can also be transferred to another site. The emissions from this process are carbon monoxide, carbon dioxide, water vapor, and NOx. If, however, we replace the coal preparation and the gas preparation with renewable energy, producing hydrogen, then we find that our emissions are only water vapor and hydrogen. The +++ indicates emissions that may come from the iron ore. So some impurities within the ore will be processed into gases and released. This will be different depending upon where the ore comes from. So the reaction pathways within a DRI from syngas. This is some work carried out by Hamada, modelling how a shaft furnace actually works using syngas. From this, we can actually see that over 60% of the reduction is carried out by hydrogen. We have hematite to magnetite, 11%, magnetite to verstite, 18%, and verstite to the iron at 33%. So it's not an unrealistic step to see that we could replace more of the CO with hydrogen as a reductant. So hydrogen can be used as part of the energy mix for significantly reducing the emissions from the steel industry, particularly as a reductant in the electrical steel route. There are many systems for hydrogen production: steam reforming, autothermal reforming, gasification, and electrolysis. To produce hydrogen with reduced carbon emissions, some systems will need to deploy CCUS if they are to continue using fossil fuels. Electrolysis can produce hydrogen with minimal carbon emissions if the electricity is provided from renewable and sustainable sources. There is no one solution to fit all decarbonisation. However, electrolysis may provide a viable option for the steel industry to become compliant with future emissions regulations. Thank you very much for your time. I will be open for any questions later, or we can meet later if I am present at the conference. Thank you very much.